Hello everyone, and thank you for joining me today. My name is Shahriyar, and I'm a PhD student in the Computing and Information Sciences program at Rochester Institute of Technology. Today, I'll be presenting our recent work on a novel adversarial purification method called IVORY. IVORY leverages diffusion transformers to tackle the challenges of adversarial attacks on facial recognition models, particularly in extracting soft biometric features like gender, age, and ethnicity from obfuscated images. As privacy concerns over online facial images grow, adversarial attacks have become a common defense mechanism. However, these attacks can often be reversed, which leads to significant privacy vulnerabilities. To investigate it further, we developed IVORY as a new approach to restore the quality of facial feature extraction while maintaining image fidelity. Throughout this presentation, I'll walk you through the motivations behind this project, the structure and methodology of the IVORY model, and the promising results we achieved. In today's world, sharing personal photos online has become second nature. However, each time a photo with a visible face is uploaded, it's exposed to potential misuse, especially by unauthorized AI-driven models that can extract personal, soft biometric data such as gender, age, and ethnicity. This type of sensitive data, when exposed, has risks that go beyond simple privacy concerns. It can lead to profiling, surveillance, and even tailored social engineering attacks. While adversarial attacks have emerged as a common method to distort these biometric features and prevent unauthorized extraction, they are not foolproof. In fact, recent advancements in AI allow adversaries to reverse these obfuscations and bypass protective perturbations. In this work, we have developed IVORY, a robust, diffusion-based purification method designed to effectively strip away adversarial noise and preserve the original facial features while maintaining privacy. This approach not only reclaims soft biometric accuracy but does so with the resilience needed to handle both known and unknown adversarial strategies, highlighting the need to develop more robust privacy protection methods for online images. In this work, we propose IVORY, a novel diffusion-based purification method leveraging diffusion transformers to effectively counter adversarial perturbations. IVORY demonstrates significant improvements in adversarial defense, restoring classification accuracy across soft biometric extraction tasks like gender, ethnicity, and age group recognition in both white box and black box attack scenarios. Our results show that IVORY consistently outperforms traditional adversarial training in DiffPure, achieving superior purification across various CNN architectures and attack methods, gaining 13.92% average accuracy in the black box setting. We show that IVORY also reduces SSIM noise by over 50% at 1x resolution and up to 80% at 2x resolution compared to DiffPure. To tackle the limitations of conventional adversarial techniques, we developed IVORY, a purification model that's distinct in its use of diffusion transformers. IVORY is powered by the Multimodal Diffusion Transformer, or MMDIT, an advanced model structure known for its success in image restoration and generation tasks. Here's how it works. IVORY takes in adversarially perturbed images, which are images that have been deliberately distorted to confuse or protect against unauthorized analysis. Once these images are fed into the IVORY pipeline, the MMDIT model applies a two-stage diffusion process. In the first stage, Gaussian noise is added to degrade the adversarial patterns. Then, in the reverse diffusion phase, this noise is gradually removed, restoring the image to a cleaner state where soft biometric features like gender, age, and ethnicity can be accurately extracted. Through this method, IVORY not only removes the adversarial noise but also reconstructs the image in a way that enables deep learning models to identify the essential soft biometric data with minimal distortion. This unique capability sets IVORY apart, allowing it to surpass existing methods in both accuracy and reliability across different attack scenarios. To evaluate the effectiveness of IVORY, we carefully designed an experimental setup that tests its robustness across various models, datasets, and types of adversarial attacks. We chose 3 leading CNN architectures known for their effectiveness in facial recognition and soft biometric classification: VGG16, CNET, and MobileNet v3. Each of these models is highly regarded for tasks such as gender, ethnicity, and age classification. For our datasets, we used VGG Face 2, a large and diverse face dataset, alongside VMER and VMAGE, which add ethnicity and age labels respectively. In the Adians dataset, known for its focus on unconstrained age and gender classification. These datasets allowed us to conduct rigorous testing under various conditions and ensure our findings would be applicable to real-world, diverse image sets. Finally, we employed a range of adversarial attacks, each with different strategies for distorting images and confusing models. Projected gradient descent is commonly used for generating adversarial perturbations. Auto attack is an ensemble of robust attacks, and Carlini and Wagner attack is known for creating strong, targeted perturbations. Together, these models, data sets, and attacks form a comprehensive foundation for evaluating the resilience and efficacy of the Ivory purification method. Ivory demonstrated impressive results across both white box and black box adversarial scenarios. To clarify, in a white box setting, the attacker has full knowledge of the model architecture and parameters, making it easier for them to craft highly effective adversarial samples. Despite this challenge, Ivory achieved high recovery rates, especially in gender and ethnicity recognition, bringing model accuracy close to clean levels. For example, under the PGD attack, VGG16's accuracy in gender recognition dropped significantly, but Ivory restored it to over 96%. In the more challenging black box scenario, where adversarial attacks are transferred across models, Ivory continued to perform remarkably well. This setup simulates real-world conditions where an attacker doesn't know the exact model structure, so they rely on adversarial attacks generated on different models. Even in these conditions, Ivory consistently improved accuracy across tasks, demonstrating its robustness and generalizability. When comparing Ivory with existing adversarial defenses, namely adversarial training and Diffpure, we observed that Ivory consistently outperformed both methods in both accuracy and efficiency. In white box scenarios, where the adversary has complete information about the model, Ivory achieved near clean accuracy levels for tasks such as gender and ethnicity recognition, far surpassing the performance of adversarial training and Diffpure. In black box scenarios, where adversarial attacks are transferred between models, Ivory's accuracy gains were even more impressive. Compared to adversarial training and Diffpure, Ivory consistently showed higher resilience, particularly in complex tasks like ethnicity and age classification. This makes Ivory a robust choice for safeguarding facial recognition systems under diverse adversarial threats. An essential measure of any purification method's effectiveness is not only how well it restores classification accuracy, but also how well it preserves image quality. To evaluate this, we used the Structural Similarity Index measure, or SSIM, which quantifies the similarity between the original and purified images. Lower SSIM noise means that the purified image closely resembles the original, which is especially important in applications requiring visual fidelity. Here, you can see the comparison across different purification methods. Starting from the left, we have the original clean image, followed by an adversarially perturbed image that's heavily distorted by noise. Moving right, we see images purified by Diffpure and then by Ivory. Notice how the image processed by Ivory retains more of the original visual details with less noise. Additionally, when combined with a latent upscaling technique called just resize, Ivory further enhances the purified image quality, making it even more visually coherent and closer to the clean original. These results highlight Ivory's capacity for high-quality purification, making it not only an effective adversarial defense but also a method that maintains the visual integrity of images. This balance of security and quality is crucial in applications like facial recognition, where both factors are paramount. In conclusion, our work on Ivory has shown that diffusion transformers can be highly effective for adversarial purification, setting a new standard for recovering soft biometric accuracy while maintaining image quality. By leveraging the multimodal diffusion transformer architecture, Ivory restores the utility of images that have been intentionally obfuscated by adversarial attacks. Our results indicate that Ivory significantly outperforms traditional defenses, including adversarial training and Diffpure, across both white box and black box scenarios. Ivory's strength lies in its unique approach that balances robustness with visual fidelity, making it well-suited for sensitive applications like facial recognition where data privacy is crucial. In addition to enhancing model accuracy, Ivory achieves impressive noise reduction, ensuring that the purified images are clear and close to their original quality. Looking forward, there are several directions for future work. Expanding Ivory to handle a wider range of attack types will enhance its adaptability in evolving adversarial landscapes. We also plan to optimize its efficiency, which is essential for real-time or large-scale applications. Lastly, integrating Ivory with other privacy-preserving techniques could further strengthen its defense capabilities, offering a more comprehensive solution for image-based privacy protection. Thank you for your attention. I welcome any questions or thoughts on our work and the future of adversarial purification.